Okay, and yeah, we're gonna post the questions afterwards on Diderot. Other than that, feel free to unmute yourselves and just have a good time. All right, let's get started.
Okay, so I'll be going over randomized algorithms. I'm gonna skip the basic review of probability and jump into the problems. But if you have questions about definitions or anything else while we're going over the problems, just like stop me or say something in the chat, and I can stop and go over it. Cool. So the first question that we're going to go over is another kind of sorting. So in lecture and presentation, we talk about quicksort. But in this problem, we'll consider linear insertion sort, which basically works by swapping elements in place until everything is in order. So you take the first and second elements, you swap them if they're out of order, and then continue to the third element, compare it with the second. If it's less than the second, then you swap it, and then repeat that with the first. So like every time you insert the kth element, you can assume the first k minus 1 are in sorted order, and you compare and swap as many times as needed so that the first k are in sorted order. So let's assume that we have a random permutation with 1 to n, and we want to find the expected number of swaps that are needed to sort the whole array. Cool. So actually, any questions about the problem statement? Okay, so usually when you're looking at expected value problems in probability, and especially in randomized algorithms, it's almost 99% of the time going to be something with defining random variables. So like indicator random variables or other just extra random variables that will make the problem easier to approach. So in this case, how can we express the total number of swaps as some function, probably like the sum of several random variables? How can we break the problem up? Does anyone have any thoughts? Yeah, sure. So someone said x sub I is the number of times you swap the ith element. Yeah, so we can consider it as a number of swaps that each element needs. So if you're considering inserting the ith element, how many swaps do you need to place the ith element in sorted order? Okay, so how would we compute? Okay, I also saw that someone said you can look at indicators for if rank I and j are swapped. That's also like another valid approach. I think the ending answer is the same, but we'll just go with like the first idea. Cool. So how would we compute the expected value of x sub I? So like, this is another place where, so like this isn't an indicator random variable, right? And you're still trying to find the expected value. So the first thing you could approach is, again, trying to break this up into multiple problems. So does anyone have suggestions for how we can break up x sub I further?
Make it x of I comma j for each j that's not I.
Yeah, sure. So we can do the sum from j equals 1 to I minus 1 of the expected value of x sub ij. And what does x sub ij represent?
Swapping I and j.
Sure, cool. Okay, so then, so x sub ij is 1 if I and j elements are swapped. Okay, so this is an indicator random variable, so the expected value of x sub ij is the probability that it's equal to 1. So then, how would we write the probability that it's equal to 1? Oh, I missed it. So what is the probability of the ith and jth element are swapped? Given that it's a random permutation of 1 to 1. Yeah, so we're summing from 1 to I minus 1 because we want to find the number of swaps to place the ith element in sorted order. So like if you consider, let's say like you're looking at the third element, for example, right? So the third element can be swapped with either the second element or the first element. But yeah, it's going to be swapped by like some number of elements from the first to second. So like you don't really consider it as being swapped with itself. I mean, I guess you could have it you could have it be from 1 to I, and then to say like except I is 0, but I think this isn't good. Okay, so someone said 1 over n minus I. Can you explain the reasoning behind that? So like remember that here I and j are not elements aren't the indices in sorted order. They're just the elements in like the permutation that you begin with. So like
what I was going to say is there's n minus I elements in the set that are unsorted after I. So that's the total size of the set we're selecting from when we're looking for elements to swap in place. No idea if that's right.
I don't think I follow. Wait, so you're okay? What I think we can talk about that later. But for now, let's focus on figuring out the probability that like. Oh, I see. So you're saying that there's like n minus I elements after I, so like j is one of those.
Yes.
Yeah. So I think that uses the assumption that you're considering the array in sorted order right now. But what we're doing right now is like just saying that you have your random permutation, and you just want to figure out whether I is swapped with this particular element that's before it. So like I think the n minus I idea works if you're considering the element in sorted order, but in this case we're not. Does that make sense?
Wait, I have a question.
Yeah.
How come we're only considering everything up till I minus 1? What about the elements to the right of I?
Yeah, so like the way the algorithm works, right, is wait, let me go back. Okay, so the way the algorithm works, right, is when you're inserting the ith element, you compare it with the first, you would swap it with the elements between 1 to k minus 1. So when we're looking at the number of swaps to move the ith element in the array to its proper place, we only need to consider the elements that are before it.
Okay, that makes sense.
Yeah. Okay, so oops. Yeah, so someone said, and someone in chat said, it's the probability that I is greater than j, and yeah, that is correct. So actually, I think it's yeah, no. Okay, so if we're sorting into ascending order, it would be that I is less than j. But yeah, like the argument is like symmetric either way. Cool. So what is the probability that the ith element is greater than the jth element?
A half?
Yeah, it's half because so like I think one way to think about it is that when we're looking over all of these random permutations, right? Like you can think of it as like placing the elements into into the slots instead of like assigning instead of trying to figure out the probability of each element being in a particular place, we only care about the ith and jth element. So like one of them is bigger than the other, and we're just looking at the probability that the bigger one is that I is the bigger one and is to the right of I is the smaller one and is to the right of j. So like that happens with probability 1/2 because there's only two possible orders for where I and j could be. It could be that I is before j, or it could be that j is before I, assuming that I is greater than j, or I is less than j. So that's why it's 1/2. So this would be the sum from j equals 1 to I minus 1 of 1/2, and that is I minus 1 over 2. Okay. Are there any questions about this? Nope. So we found that the expected value of x sub I is I minus 1 over 2. So then how would we figure out the expected total number of swaps? Yeah, exactly. So you'd sum from I equals 1 to n of the expected value of x of I. This is using linearity of expectation, and then you get I minus 1 over 2, and this comes out to n times n minus 1 over 4. Yeah, I can go over that if necessary. We don't really have to sum over I. What do you mean? Yeah, if you do each pair individually, it's the same thing. Each one has 1/2 probability. Yeah. Yeah, so like another approach is to define, it's just like instead of looking at how many swaps it takes to move the ith element in sorted order, consider all pairs x, I, j, and then let this be 1 if the ith and jth element are swapped, and that happens with probability 1/2. And then, so then like the total number of swaps would be the total number of pairs times 1/2, which is n choose 2 over 2, which is the exact same answer. Cool. Yeah, so that's that problem. Are there any questions about this one? Okay, so the next problem is bamboo cutting. So we have a bamboo stick, I guess, of height n meters, and we choose to cut off x meters of it in one step. And x is some uniformly randomly chosen integer from 1 to n. And we want to prove that the expected number of steps we need to chop the entire bamboo is O of log n. So the way that we can think about doing this is, so if we let x equal the number of steps to cut off the whole bamboo stick, so the first step is we can show that the expected value of x is O of log n with high probability. And then in the next step, we can use the law of total expectation to show that it must be O of log n. Are there any questions about why we're splitting it up into these two steps? Oh yeah, sorry. Okay, is it okay to? Yeah, thanks, Stephen. Cool. All right, so let's start with the first step. So we want to show the expected value of x is O of log n with high probability. So like we did in class with quick select analysis, let's reason about the expected reduction in the length of the bamboo stick after one step. And then we can figure out what the expected length of the bamboo stick would be after some number of rounds k. Okay, so how do we compute the expected size of, actually, does anyone have any guesses for what the expected reduction would be?
Isn't it just half?
Yeah, it's just 1/2. Do you want to explain why? No.
It's because you uniformly pick the cut from 1 to n. So like the expected value you're gonna get from that is just the middle, so n over 2.
Yeah, it's actually n plus 1 over 2 because it's from 1 to n. Like it's the expected reduction is about 1/2. Yeah. Okay. Does anyone want to see that more formally? Okay. Cool. So the expected reduction is 1/2. Okay. So then let's let S of k be the size of the bamboo stick after k rounds. So then using induction and the claim that we made in the last slide, we know that, oh, it should be S of k, by the way. We know that the expected value of S of k is n times 1/2 to the k. Okay, so then how would we show that the expected value of x is O of log n? So what should we let k be? So k equals log n. We can try that. Let's see. So s of log n, and then we would say that this is greater than or equal to 1. So then by Markov's, what would this be less than or equal to? Does everyone remember Markov inequality? Probability that x is greater than equal to a is less than equal to the expected value of x. Yeah, I guess since I wrote it down, I'll just say it. So this is the expected value of s log n. Okay, so what would this be? Okay, so this is n times 1/2 the log n, which is n times 1 over n, unfortunately. So k equals log n doesn't work. Does anyone know how we can change k so that so that we can show that this is less than or equal to 1 over n? Yeah, sure. We can say k log n. Yeah, 2 log n, yeah. So for high probability, it's supposed to be 1 minus 1 over n to the k for some k. But for our purposes, I think we can just prove that it's less than or equal to 1 over n. Yeah, so if you let this be 2 log n, then this comes out to n times 1 over n squared. So this would be 1 over n. So you've shown that the probability that that you're still going on after that the bamboo stick hasn't been completely chopped off after 2 log n rounds is less than or equal to 1 over n. Are there any questions about like how we prove this? Okay, so that's using that. Okay, so now we want to show that the expected value of x is O of log n using the law. Yeah. Wait, sorry. Which slide do you mean? If you're talking about the Markov's proof, that's it's like the same thing here. I just like cleared it up.
Oh, okay, thank you.
Yeah. If you wanted to prove from the second line to the third line, yeah, let me do that out. So it's n times 1/2 to the 2 log n. We assume that the base of the log is 2. So this is n times 1 over 2 to the 2 log n, right? So then we can say this is n times 1 over 2 to the log n squared. And then 2 to the log n is n. Yeah, so this would be 1 over n times 1 over n squared. Is that okay? Cool. Yeah, it's not the same k. Sorry, I probably shouldn't have picked k as the number of rounds. Okay. Cool. All right, so let's go back to proving that the expected value is O of log n with a law of full expectation. So like, if you recall from homework and lecture, we talked about the ideas of good and bad events. And so like, I guess the motivation behind this is once you have a high probability bound, it pretty easily translates into like a bound for the actual expected value, because you've just shown that like the bad case is really unlikely to happen. And so like to make this more formal, we need to define a good event and a bad event. So what should our good event be? Something in something about x, right? Because we just proved the bound for x. Yeah, exactly. X is less than or equal to 2 log n. It's less than or equal to 1. Sure. So this is, we should need some x up. Yeah. So we can let less than or less than or equal to doesn't really matter. I just made it less than because then the bad event is exactly what we proved in the high probability bound. Cool. Okay. So okay. So now we want to figure out what the expected value of x is. So here we're just using the law of total expectation. So you can write the expected value of x as the expected value of x given good times the probability of good. plus expected value of x given bad times the probability of bad. Okay, so how can we, okay, so what do we know about each of these things? So what can we say the expected value of x, given that it's good, is less than or equal to? Does everyone follow like how we define the good event and the bad event? Actually, let me write it out.
So it'll just be 2 log n and then probability of whatever we got from earlier.
Yeah, so this is 2 log n.
One
Okay,
minus 1 over n, I think it was.
yeah, so that doesn't really work, right? So like the reason it doesn't work is because we show that the probability that it's bad is less than or equal to 1 over n, right? And then the probability that it's good is equal to 1 minus the probability that it's bad. So then all we know that is that it's greater than or equal to 1 minus 1 over n. But here we want to show an upper bound for the expected value of x. So you can't bound it by 1 minus 1 over n. Okay, we can come back to that one. But so what should
bounded
be
by 1 then? Just bounded by 1, which because it
yeah. Yeah, exactly. Yeah, you can just bound it by 1 because all probabilities are less than or equal to 1. Okay, so then what is the expected value of x given that it's bad? What can we bound that by?
n, because we remove we don't ever remove 0 thing.
Yeah, exactly. So at every step you're guaranteed to put up at least 1 meter. So you know that the absolute worst case that x could be is n. So the expected value of x given that it's bad also has to be less than or equal to n. Okay, and then what is the bound for the probability that it's bad? Actually, I already wrote here. So we know that it's less than or equal to 1 over n. So we can put that here. Cool. So then this is equal to 2 log n plus 1, which is in both log n. So now we've proven that the expected value of x is always log n. Okay, any questions? Going to the next slide, it just has like the actual, it just has it also written out here. Yeah, so we didn't get it was equal to 1 over n. We know that it's less than or equal to 1 over n. So like if you remember in this slide, right, we showed that the probability that we showed that the probability that you're still going on after 2 log n rounds is less than or equal to 1 over n. So then that means that the probability that x is greater than or equal to 2 log n is less than or equal to 1 over n. Is that okay? Okay. If that's all the questions, then I guess we'll move on to the next part.
Is the next part me?
I think so.
Yep.
Okay, cool. Sweet. Can you guys see my screen?
Yep.
Awesome. Let me open the chat just so I can see if anybody has questions. Okay, cool. So I'll be going over the substitution method. And we're just going to work with this example that you see on the slides right here. Wn equals 2 times Wn over 2 plus O of n. Cool. So for a substitution method, as you guys know, we have basically 2 main steps. Step one is guessing a big O bound for the recurrence, and then step 2 is using the substitution method to actually prove it. And probably we don't want just a wild guess. We want some guess that we're pretty sure of, so that way we're not running this substitution method over and over. So does anybody know of a good way to come up with a guess for this recurrence?
multiple of m squared, probably?
Not quite n squared. Okay, somebody in the chat says n log n. So we're gonna see that it does end up being n log n, but one good way that I think I like to use to do the guess is to use the brick method or the tree method. This usually gets us a pretty good guess, which then we can prove using the substitution method. So if we run through this with the brick method, pretty simple. We have the work of the parent is n, each of the children is 2 times n over 2, which is n, so we get balanced. And since each time n is decreasing by 2, or decreasing by a factor of 2, we get logarithmic depth times n work per level, which is n log n. Yep. So now with this guess, we have what we need to get started with the substitution method. And just for this method, we're actually going to rewrite this recurrence as k times n instead of O of n. Just so the math works out, we have constant. Why would we need to use the substitution method? Just so that we can mathematically prove that this recurrence is in this n log n bound. Does that make sense? Yeah, so brick method is like a shortcut we use to get to the approximation of a big O bound, but to mathematically prove it, we use the substitution method. Yeah, I think Sanjay's providing an answer in the chat as well for that. Okay, let's keep going with this. So now that we have a guess, step 2 is to prove. So we have for substitution method, proof by induction. So 3 main steps. And actually, first let's define what we actually want to prove. So somebody mentioned in the chat that O of n log n can be written as some constant k1 times n log n plus some other constant. So this is what we have, right? We have Wn is less than or equal to k1 and log n plus k2. This is for input size n greater than or equal to 1, and for some k1 and k2 constants. Daniel asks, how do we know that our guess is wrong? We're doing the substitution method, and someone responded, the proof will fail. Yep, that's correct. So in this case, we have a pretty good guess. So I'm quite sure that actually, well, I know that our proof will not fail because I've written the slides for these. So yeah, if you somehow, you can do this as an exercise actually if you want. Try like a completely incorrect guess for this recurrence, and then you will see somewhere down the line, our induction proof will not be able to keep going. Okay, so the key thing with the substitution method is we come up with this I guess equation that we want to prove, and we come up with these constants which we don't know yet. So we're just going to go ahead with the proof assuming that these are correct, and at the end of the proof we'll have some equation where we can plug in what these constants are, and it'll make the proof work. Okay, so step 1, we have the base case, which is input size 1. Okay, so we have this base case input size 1. Can someone either say or type in the chat what we expect this to equal?
It equals k, and we just need to say that k2 is bigger than k, bigger than or equal to k.
Yeah, that's absolutely correct. So if we just plug it into our original recurrence right here, we don't need to worry about the recursive case because it's the base case. We just have k times 1, and we can show that's less than k1 times 1 log 1 plus, oh, that's a typo. That should be k2 right there. But yeah, so if we do the math here, we get k is less than or equal to k2. And so when we're picking k at the end of our proof, or we're picking k2 at the end of our proof, we should make sure that it works for this equation. Cool. So next we have our inductive hypothesis in our induction proof. So I want to take a stab at what the inductive hypothesis will be.
You can say W of n upon 2 is upper bounded by k1 times n upon 2 times log of n upon 2 plus k1.
Yep. So we have the next smallest input besides n, which is n over 2. And we're just going to assume that the proof holds for this case. Great. So now we have our inductive case, and we start with our recurrence equation. Wn is less than or equal to 2W n over 2 plus Kn. Actually, this would be equals because that's what we have here. But we'll see that soon it'll become less than equals. Okay, so this is directly taken from our given recurrence. And now what we can do is we notice that this Wn over 2 case is given in our inductive hypothesis, so we can plug that in. And this is basically always going to be the case. We can plug in the inductive hypothesis into the inductive case to get some equation that we then solve. Okay, cool. So we plug that in from right here, and what we can do is we can see that we can distribute the 2 in, multiply it into this k1 n over 2 log n over 2 term, and also this k2 term. The 2 and the 1 over 2 cancels out, so we have just k1 n log n over 2 plus 2 times k2 plus kn. So here there's something else that we can notice is we can use the log rule to break up this log n over 2. So now we have k1 n log n minus log over 2. And log over 2 is just 1. Sorry, log of 2 is just 1. So now let's do some more math. We can multiply the k1 n into the log n and the negative 1 to get k1 n log n minus k1 n and the rest of this expression. From here, we notice that what we want to prove is this recurrence, or this equation here that's highlighted in blue, Wn is less than or equal to k1 n log n plus k2. And we can actually find that in our inductive case here, hidden somewhere inside this equation. And this is basically a pattern you'll see in basically any sort of, in most of the substitution method problems you'll see. You'll basically get exactly what you want to prove plus some other stuff, and then you can show that it's bounded by something that makes sense to us. So how can we do that here? First, let's rewrite it so that we have this k2 moved closer, so that way we can see this is indeed k1 n log n plus k2 and some other stuff in the back. And since we want to bound this by this k1 n log n plus k2 term, the extra stuff has to be negative, right? If it's positive, we can't really bound it because Wn might be bigger than k1 n log n plus k2. But if everything here is negative or 0, then we can say that Wn has to be less than or equal to k1 n log n plus k2. And this is where we actually can come up with some constants k1 and k2 that work for this equation. So we want to come up with constants k1, k2 in terms of k that make this red part of the expression negative. And keep in mind that we also want it to work for the base case. So does anybody have some suggestions on what k1 and k2 could be? K and K. Yeah, so that'll work, I think. So that's actually what I have here. If you notice, if we plug in k2 equals k for the base case, we get that k is less than or equal to k, which is always true. If we plug in 2k and k for k1 and k2 into this bottom part of the expression here, we get, I think, negative 2kn plus k plus kn, which for input size n greater than or equal to 1 will always be either 0 or negative. So using these constants, we can show that Wn is indeed bounded by k1 n log n plus k2. So we have proved that this recurrence is O of n log n. Cool. Any questions now that we finished?
I had a question.
Yeah, go ahead.
Do we have to find K1 and K2? Like, do we have to do this, find K1 and K2, then go back and like plug in our K1 and K2 and show it works? Or can we just end here?
You mean like if you're like on a test, you want to make sure that like we understand that it works?
No, like we've shown it works here, right? But like
Mhm.
once we picked K1 and K2 at the end, do we have to like, as like another part of our proof, do we have to like plug it back in and show it works, or can we just end here, like for points?
No, so we kind of pick K1 and K2 at the end, but in terms of the proof, we can assume that K1 and K2 have already been defined. So we can look at the proof with K1 and K2 already being defined.
Oh, so we can just like leave it in terms of K1 and K2.
Yeah, so this is basically fine. If you write it this way, this works. Does that answer your question?
Yeah, that's fine. Thank you. It was just
Cool.
that like we didn't really go over it fully in lecture, so I was a little confused.
I see. Okay, no worries. Any other questions? Why the red part has to be negative? Okay, so let's say that this red part is positive. Then we no longer we no longer know that Wn is bounded by upper bounded by k1 and log n plus k2, right? Because it could be k1 and log n plus k2 plus some really large number. So we don't know that it's smaller than k1 and log n plus k2 anymore. But if this red part is negative, then we know that Wn still has to be less than or equal to k1 and log n plus k2. So it's still in log n, right? Sweet. Any more questions? Okay, awesome. Yeah, so to practice this, I would recommend just coming up with a recurrence and then just going through the process and trying to prove it. That's basically what I did to come up with this example. I just thought of some recurrence and then went through all the steps and turned out pretty well. So yeah, that's it for me. If somebody, I don't remember who's next. Algorithm design.
Yeah, I think I'm next. Awesome.
Hey, what's up, Anish? Welcome back.
You probably don't recognize me, but I'm actually a former TA, so I'll be going over a short divide and conquer problem with you guys.
Anish was the head TA last semester. I miss you, Anish.
Every day. I think host disables attendee screen sharing, so you may have to.
Oh yeah, I got you. Hold up. Let's see. Make co-host. Okay, there you go.
All right, I got you. Thanks. Cool. All right, yeah. So we're gonna go over a quick divide and conquer problem. Again, like this is really weird, like in a virtual setting. So if you have questions, just like feel free to unmute yourself and just like ask me or put it in the chat, like you've been doing this entire time. But awesome. So this is the question. So basically, you have a list of stock prices on n different days, and you can buy a stock on some day I and sell it on some day j. So you have to buy it before you sell it. That's why I has to be less than j. And you need to find the pair ij such that you maximize your profit. You can make only one transaction. So you buy once and then you sell once. And you want to figure this out in O of n work and O of log n span. So like for an example over here, we have like these stock prices 6, 7, 8, etc. So the best day to buy it on is on day 3, which is 0, 1, 2, 3, which is over here. So you buy it at $1 and then you sell it on the last day at $5. And that gives you a profit of $4. You can try it with different pairs and you'll find that that's the best possible pair to buy and sell to maximize your profit. So your goal here is to use divide and conquer to basically solve this problem in a parallel fashion. So I'll give you a few minutes to think about it. Ask me any questions if anything is unclear.
Would people actually, like, I know some people hate breakout rooms, but would people enjoy being put in breakout rooms to speak with other people about this? You could just do a yes, no in the participant chat. And we'll just take a majority vote. Nice, wow, people really hate the breakout rooms. Yeah, that's why I asked, no worries.
All right, does anyone have an idea of how to solve this problem, or is anything unclear?
I guess I'm not totally sure why you would use like dividing. It seems like you could do it with like a scan as opposed to doing divide and conquer instead. Like you could reverse it and scan from left to right, or I guess scan from right to left in the original thing.
Yeah, I think Cooper, you basically got it. That was actually part 2 of this question of how to use scan to solve this. And yeah, you can do it with 2 easy scans. You scan left to right with min, and then you scan right to left with max. So then at any given point, you know the minimum price and the maximum price for, on that day, and you can simply solve this problem. But let's try to solve it with divide and conquer for now. So let's try to figure out how you can split this entire array in 2, and then how you can combine them. So how can you strengthen the problem using divide and conquer?
Strengthen the problem.
Sorry, I didn't hear you.
Strengthen the problem.
Yes, yeah, strengthen it. For example, like in Paren Lab and MCSS Lab, you strengthened the problem by adding more information, right? Like I think it was the max prefix sum, the max suffix sum, like that. What other information do you need to store to solve this problem?
The minimum and the maximum.
Yes, that's correct. Do you want to explain how that works?
For each part, it gives the min, max, and what you currently need that at a certain one. You can have like 3 in 1, so the min would be 1, the max would be 3, and the current best is 2. This is in case we have something like an 8 in the middle or something like that, so that we can only have 2, but
Right, exactly, yeah. So basically, if I were to split this array in 2, so like let's say we had 6, 7, 8, 1 on the left side, and 2, 3, 4, 5 on the right side. Clearly, like 6 and 8 is the best transaction to make on the left side, and on the right side, 2 and 5 would be the best transaction to make. But when we combine those 2 sides together, we're not really sure how to combine that information. So what we also need to store is the minimum and maximum. So our combine function is going to take into account what the best solutions on the left and right were. But moreover, it's also going to take into account what the minimum and maximum prices were. So you can take the max across the solutions you've already found on the left and right. And you'll also take the max with the minimum solution on the left side and the maximum price on the right side, because that's one other type of transaction that you can make. And you need that extra information to account for that. So quickly just going over like how this combined step works and how you should probably think about it during an exam setting. Basically, like this is how I think about like divide and conquer in general, like this is a pictorial diagram. You basically split up the problem until you hit some sort of base case, and then you're going to combine those base cases together using this combine function that you define until you find the solution to that final problem. So in this case, this is just merge sort. I'm basically splitting up this array. I need 2 splits to get it down into singleton elements, and then I sequentially combine them together in order to solve the merge sort problem on this giant array. And when you're thinking about combine, you want to think about, just given these 2 subproblems and given their actual solutions, what else do I need to solve this actual problems, to solve what the problem is asking for? So in this case, if we just stored I and j, which was the best time to buy and the best time to sell, you can't really combine that information with another I and j solution on the right side of this array. Like you need something else. And I think Poon, if that's how you pronounce your name, brought this up. And he said if you store the min and max, then you can think about that other transaction that you can make. So buying the minimum price on the left side and selling at the maximum price on the right side, which is a transaction that you can also account for. And that's how you have to strengthen this problem. So you'll store 4 things in total. You'll store ij, which is the best solution to the current subproblem that I'm solving, but also the minimum value in the subproblem and the maximum value in the subproblem, so that I can solve problems that I combine with in later steps of this whole divide and conquer process. Exactly. So I think Eric also put this in. He said min, max, and then the best answer out of this interval. Perfect. All right. Any questions on how this works? All right, awesome. And I think Cooper also pointed this one out, but how can we use scan to solve this problem? You're basically going to use scan twice. You're going to go scan front to back, basically from left to right with the min. So you want to find the minimum value sequentially from the left side to the right side of the array, and then you want to find the maximum value in the reversed version of that array, so that at any given point you can find the minimum value to the left of me and the maximum value to the right of me. So then you know exactly which transaction to do. So after finding the min and maxes, you'll just walk through that scanned array and figure out what the best transaction time was. All right, any questions, or are we good to move on to the next topic? All right, cool. It seems like everyone got that one. So I'll hand it off to Cam here.
All right, cool. Thank you so much, Anish. Thanks for teaching that. So let's go on to the next problem. I will share my screen. Okay, cool. So now we're going to do, everyone can see my screen, right? We're all good? I can't see anyone.
Yeah,
it looks good.
All right, cool. So there's no surprise for Cooper to run this time. This is just a basic problem, like a simple algorithm design problem with one layer. Essentially what we have is, given a sequence of n integers called nums, we want to return an array called output, such that every index of the output is the product of all the indices, the product of the elements at all the other indices. So take a second to think about that. Okay, so I'll repeat that. You take in a sequence of numbers and you want to return an array such that at every index, that element represents the product of all the other elements, not including the element. And we want to do this in O of n work and log n span, and we want to do this without the division operator. Okay, so meaning you're only using, or you can use anything besides division. So any initial ideas on how to solve this?
One of my initial ideas is map index, but I think that becomes O of n squared work, so that doesn't work, I don't think.
Oh, so you want to map the index to the multiplication of the
Yeah, so like
elements.
have a base case of all ones and then just do map IDX on it, but I think that's O of n squared.
Yeah, that's a good brute force algorithm. But yeah, it's O of n squared.
Could you perhaps just scan one way, scan both ways?
Okay, so what was your motivation for using scan?
Well, I guess it just immediately came to me that if we don't want to multiply I, we just need the product of everything smaller than a product of everything before it, like after it.
Great. Yeah. So I think a lot of students have trouble like understanding why is scan useful. Like it seems like this random algorithm that we throw out to you, and I think understanding the motivation and intuition of why we really use it and why we love it is important. So what you said is, yeah, we can assume O of 1 for multiplication. So we're using scan because what you want is the product of every element before a certain element, oops, and the product of every element after a certain index. So if you think about that for a little, that seems like you're accumulating products, right? And then that's when scan should hit. You should be like, oh wow, we're just doing a function over and over again on these elements, and we want to keep track of that as we go through the array. So let's say our input array is 1, 2, 3, 4. As the student suggested, we're going to do a forward scan. So we're going to put the base case of 1 initially. Then we have 1, 2, 6, and 4 is out here. Oh, sorry, the multiplication of 4 and 6. So 24 is out here, which we're not going to need. Then we're going to scan backwards. So if you scan backwards, it goes this way, and you just reverse the array. So this is what you get. What this means is that the element at every index is equal to the multiplication of all the elements before it in this array and after it in this array. So if there's no elements before it, we just get the base case. If there are elements before it, we get the multiplication of all the elements. So for example, let's look at index 0, 1, 2, 3. We have 6. So if we go to index 0, 1, 2, 3 in here, let's take a look at everything before it. 3 times 2 times 1 is 6. That's how we get the 6 here. And so same idea here, except it's from the other way, in front of it. So now if we want to just get the multiplication of like both sides at a certain index, what do we need to return in the output array? In terms of like code or in terms of the index I?
You can just zip your, just zip the two things with multiplication.
Yeah, perfect. You're just going to multiply all these together, and then that'll be your output array. Okay, Poon, I think you have a question?
Yeah, I wanted to ask, are we using scan include for scan backwards? Is that how we're getting, or how do we get 24 as the first one?
Good question. So you're scanning forwards this way and then reversing the result. So if we scan backwards, reverse this array, you get 4, 3, 2, 1, and then you put in the base case, then you put in 4, then 4 times 3 is 12, then 4 times 3 times 2 is 24, and then the results will go over here, and then you reverse that array. Does that make sense?
I think so, yeah.
Okay, yeah. So what you're doing is reversing the input array, running scan, and then reversing the output result, and ignoring, of course, the final product. Okay, fantastic. So now we're going to put this to code. So since this piece of code is not very long, I actually want you to, if you have a piece of paper, write it out, because sometimes we do ask you to write pseudocode in the exam, and it's not trivial to take a theoretical idea to code. So it's good practice to get to do that. I recommend you take out a piece of paper, take 2 seconds, and try to write down the code for this. You can use pseudocode. Like to reverse an array, you can just write rev, R-E-V.
Can we just say like scan L or scan R on the on the exam for pseudocode?
What is the difference between scan L? Oh, like scan inclusive and non-scan?
No, scan from the left, scan from the right.
No, you have to do the reverse because
we have to explicitly reverse it. Okay.
Yeah. I mean, it's just one extra line of code.
Yeah. Is there any reason the signature just doesn't do scan L and scan R instead of just scan?
I don't know actually. Should ask Sam. There's probably a reason for it. Okay, does anyone want to share their code with us?
Make a tuple called x comma underscore equals scan whatever input is. I call it s.
Yep.
Y equal rev s.
Mhm.
B comma underscore equals scan y, and
Yep.
then rev c again, and then tabulate function something equals seek dot nth seek dot nth for x multiplied by seek dot nth for y for the length of either one.
Perfect. Yep, that's pretty much exactly what we had. So forward scan, backward scan. Notice how we're scanning on rev s here. And then you take the result and you reverse it again, the result of the second scan. Again, the reason we're reversing the result of the second scan is because otherwise your output would be 1, 4, 12, 24, and then the extra tuple of 24. You want to reverse this. So that's why we rev that again. And as Poon said, we then do a tabulate. So at every index, we just multiply the other index, and that's it. Cool. Any questions on this problem? Okay, we're going to move on to Stephen.
Okay, yeah, I'm gonna share my screen real quick. Okay, so can everyone see that?
Yep.
Yep.
Okay. All right, so we're gonna start by talking about analyzing the costs of different sequence functions. So in particular, like we give you like basically the cost as long as the functions you give these functions are constant. But when they're not in constant functions, we have to do like additional analysis to determine the work and span. So in particular, we're going to go over using iterate, reduce, and scan with seek.append. So seek.append has O of like size of A plus size of B work, where A and B are the two sequences that are appending. So here, this is basically like flattening a 2D array, right? So if you have a sequence of sequences, we're appending all of them together using these three different functions. So throughout this, we're going to say that the size of the outer sequence S is n, and the maximum size of any inner sequence is m. Let me also pull up the chat so I can see that. Okay. All right. So let's start off with the work of iterate. So with iterate, we can write the work as just the sum of whatever the work of the function is for each iteration. So at iteration 0 all the way to n minus 1, basically. So the function that we're using here is append. And so the work of append, it's going to be applied to b sub I and the ith element in our sequence. So since the work of append depends on these two, the length of these two inputs, we need to determine these two lengths. Okay, so we know that S of I is, or the ith element in the sequence is at most m. That's from our initial assumptions. But what is the length of B sub I? So first of all, before that, I guess, what is B sub I here? Does anyone have any ideas on that? Yeah, so like Joanna said, B sub I here is like our aggregate that we've computed thus far. So in this case, it's the first I sequences of S appended together, or everything from S at 0 all the way to S at I minus 1. Okay, so now that we know what B sub I is, what is the length of that? Well, if it's just the first I appended together, each of them has length at most m. So that means that the total size of this is going to be at most I times m. Is that clear for everyone? Okay. think I lost the slide here. Okay, well, so after that part, we're going to end up with a summation of, let me see if I can draw on the screen actually. Okay, so we're going to replace this with I, that's not working. Okay, we're going to replace this work of append with I times M. Or technically, I guess it's I plus 1 times M, because we are appending a length I times M sequence and a length M sequence. So the work of that is the two added together. So we have this summation. To simplify the summation, we can pull the M out, and then this sum from I equals 0 to M minus 1 of this just becomes, it's O of N squared. It's actually, I think, like N times M plus 1 over 2, but that's O of N squared. So the overall cost would be O of N squared M. Okay. Does that make sense? Okay. Let me clear this and move on. Okay. Hopefully, I'm not missing any other slides. Okay. So let's talk about the span now. We can again write out the span the same way, except instead of the work of append, we're using the span. And so the span of append is constant, O of 1. So that makes our life easy. Then we're just adding a bunch of constants n times. So the overall span is just O of n. So this is something that can be a little misleading at first. So seek.iterate itself is, I guess, like purely sequential, right? So you might think that the work and span is always the same. But if the span of this function that you're using, like append here, is like cheaper than the work, then you can still get different work and span when using iterate. Okay, let's move on to reduce. So we're going to assume here that reduce is implemented using divide and conquer. So we talked about you could use either contraction or divide and conquer to implement reduce. We're going to use divide and conquer, and then for a contraction thing, we're going to analyze scan, basically. Okay, so since it's divide and conquer, we're basically just recursing on the entire left subsequence and the entire right subsequence. So each of those has size n over 2, and there's 2 calls of that size. So we can write our currents like this in terms of the overall size of S and the size of the inner sequences. And you'll notice that the size of the inner sequences doesn't change because there's still at most m when we recurse with divide and conquer, right? Okay, so this is like our recursive cost, and then we have an additional cost after we recurse and get the appended values. We have to append these 2 results together. So that's plus the work of append on that. So what will the work of append be in this? For this?
Do we have to like consider the worst case of append now?
What do you mean by a worst case? Like, I guess, yes, assuming like, so, like if you mean like worst case as in every possible set of inputs that we could have to append, which one gives us the highest cost, then yeah, that's what you should consider.
Reduce doesn't get bigger, does it? So it's still just O of m plus m, right? No.
Okay, so the 2 recursive calls gives us like the first half of the sequence appended together and the second half of the sequence appended together, right? So, or yeah, I guess what is the size of the first half all appended together, and what is the size of the second half all appended together? Yeah, I think Poon had it. So it's O of nm. So like the first half of the sequence, there are n over 2 sequences, each of length m. If we append all those together, we'll have length nm over 2. And the same thing happens for the second half, right? There's also n over 2 sequences, each with length of at most m. When we append all those together, we'll have length at most nm over 2. And then the work of append is just those two added together. So that gives us nm, which is O of mn. Does that make sense for everyone? Feel free to interrupt me at any point if there are any questions. Okay, so yeah, we get O of mn for the work of append here, and that gives us this recurrence to solve. Okay, so solving this recurrence, just using the brick method, any arbitrary parent node is going to be nm work. The cost of its children is, so it's 2 times n over 2 times m. So these 2's cancel out, so it's just also nm. And so this is a balanced recurrence. There are log n levels because we're having n each time. And the max cost of a level is nm. So the overall total cost is mn log n. All right. Okay. Looks like there's no questions yet, so we can move on to span. Okay, so again, using divide and conquer for reduce, we can look at the span of append. We have the same recurrence, except instead of 2, we don't have the 2 in front of this anymore because both halves can be done in parallel. So we just have the span of 1 call. And we also have the span of append. So here, again, span of append is constant. It's O of 1. So we get just this recurrence. If we use the brick method again on this recurrence, I'm not going to go super in depth, but it ends up being balanced. And the number of levels is log n, so the total cost is also O log n. By the way, since the span of append is constant, these costs that we find using this analysis should be the same as the library costs for reduced using like constant. So like for iterate, I think we got O of n, which is what we wanted, right, for a constant span function. For reduce, we got log n here, which is also the same as the library cost for a constant span function. And then we'll see for scan. Okay. All right. Any questions? So, oh, yeah. Is there a question? Yeah. Go ahead.
I wanted to ask why we couldn't just multiply like the work of the O1 with the work instead, because that seems to be how it turns out most of the time, where it's like just nm log n. Why couldn't we just work out the work of the append and then just multiply by the O1 cost of reduce, for example? Right,
The work of append and the work of, could you, so
times
oh, I can see chat. Okay. O of nm times reduce.
The textbook reduce.
Oh, I see. Okay, so I guess like in this case, it ended up being sort of like that. But like in general, we don't know it's going to work out this way. So I guess first of all, like work of append is only dependent on the two, like it's dependent on the two input sequences. So it's like size of A plus size of B. In this case, we're appending like a bunch of things. So to get nm, I guess, are you just doing the n times m because m is the max, and then we're like adding them all together?
Yeah.
Yeah. Okay. Yeah. So I guess in this case, it works out to be that way, but in general, that might not always happen. So sometimes we might end up getting like a root dominated case where it would just end up being the cost of the parent. So we do have to sort of go in depth into what exactly the algorithm is doing to make sure we get like the tightest bound, I guess is.
Okay, that makes sense.
Yeah. Okay, so I think we were on scan. So let's dive into scan. So scan is implemented using contraction. So we can divide the work into basically the 3 steps of contraction. There's the recursive step, the contraction step, and the expansion step. So what is the work of the recursive step? Well, for that, we can just ask ourselves, how do our inputs change, right? After contracting, we're left with n/2 sequences. So remember, contraction step, we just take every pair of sequences and sort of apply the function to those pairs. And so after that, we end up with half the original. Each of them, let's see. I think there's a typo here. Yeah, I think you are correct. This should be 2m after contracting. Yes. Okay, I believe this will mess up the later slides, but we will correct that on the fly. Okay, yeah, so after contracting, each should have length 2m because you're appending 2 together. So the work of the recursive step is just work of n/2 and 2m. Okay. And then, okay, let's look at the contraction step. What is the work of the contraction step? Yeah, I guess, does anyone have ideas on that? Two m times n/2. Yeah, I think that's correct. So there's n/2 calls to append. And these are just on sequences of length m because they're just taking from the original sequence s. And so the work at this step is just O of nm. Okay. And then let's look at the work of the expansion step. So the expansion step also makes n/2 calls to append, but now the different input sizes to append are different for each of these calls. So what are the input sizes to each call? As a hint, so the expansion step, we first recurse on our contracted sequence, and then we expand by calling our function, in this case append, on each of these elements in this sort of result we got from recursing with one of the elements in our original sequence S. So we'll be calling like append with S0 and something from S, S1 and something from S, and S2 and something from S. So these are the n/2 calls to append that we're making. So what is the length of each S sub I in this sort of intermediate scanned sequence that we have?
Should be I times m, right?
Could you repeat that?
It should be I times m, right?
Almost, right? So S sub I is like the first 2 I sequences of S appended together. So remember, like we contracted. So then when we scan on this, it's like the first each element in our contracted is like representing 2 elements of our original. So then the ith element in this sequence here is the first 2 I sequences of our original appended together. So each of those has length at most m. And so S sub I has length at most 2im. Okay. So the ith call to append has the work of 2im plus m. So since the other thing we're appending is just something from the original sequence, it's just at most length m. So this is, we can rewrite this as 2i plus 1m. I'm just factoring out the m here. And then the total cost of the expansion step is just the work of expansion. That's the sum for each of these calls so of 2i plus 1m. I'm not going to get into the specifics of this summation, but basically this works out to be O of mn squared. Okay. And then overall, we get our recurrence to be this, which I need to fix now because this is an image, so I can't really fix that. But okay, I will write on this slide then. Okay, so this should be 2m. So should this. So we have our work of our recursive step here. We have the work of our expansion step and the work of our contraction step. In this case here, the expansion step dominates the work at the contraction step. So we'll just consider that for our final recurrence. So solving this recurrence, we should get balance. Could we go back to the sum for the expansion? Yes. So yeah, this sum. Is this covering the? I have a pop-up down here. That might be.
I had a question.
Yeah.
So here, should we mention that like so obviously we append n over 2 times in the expansion, right? And we append a sequence of length 2im to a sequence of length m. And obviously that's why each call to append has that work. But do we need to mention that like just copying the element has O of 1, so then like it gets like this append step dominates it?
Copying the element?
Like copying the elements from the result from scan.
Oh, yeah. Yeah, maybe like write like one sentence, just sort of just something that, because that's usually not going to be relevant to the total cost. But yeah, you're correct. So like these appends are for like the odd indices in our final array or our final sequence. For the even indices, we just copy over this stuff, which can be done in O of 1. Okay. Okay, so all right, so originally I didn't have this 2m here, so I think it messed up this recurrence, but now with the 2m, when we solve it, we're gonna get n squared m for both the parent and the child, I think. So it'll end up being balanced. Balanced. Okay, so since it's balanced, the max cost of a level is n squared m. The number of levels is log n, since we're still having n each time. So the overall work will be n squared m log n. Okay, does that make sense to everyone? I'm sorry that this slide is messed up, but yeah, there should be an extra log n term here.
I think it's still redundant.
Is it? Okay.
I'm pretty sure you still get n squared m over 2.
Okay, maybe I shouldn't check. So the work at the parent is n squared m. The work at the child is n squared over 4 times, oh, you're right, times 2m. So that's n squared m over 2. Okay, so the slide is right. I just didn't have the 2m up here. Okay. Yeah, so because this n over 2 ends up getting squared, this bottom factor becomes 4. And so that outweighs this 2m. So it still is root dominated, it's n squared m. Okay, yeah. Sorry if that part was confusing, but does this make sense to everyone now? Okay. Okay, hopefully that didn't muddy things up too much, but let's continue on here. Okay, so let's see. Yeah, let's do the span now. So again, since append is constant span, we're going to expect this to have the same cost as our library definition for those of constant span. So if we look at the span of each step, now at the contraction step, we have n/2 appends, but each of these can be done in parallel. And the span of contraction is also O of 1. So the overall the span of append is also O of 1. So the overall span is just O of 1 for the entire contraction step. For the recursive step, it's very similar. It's basically the same thing as work, except it's span of n/2m. Or I guess this is again 2m. But yeah, it should be 2m. Let me just rewrite this entire thing. Okay. And then for the expansion step, again, since append is O of 1 constant span, now basically we can again do all of these appends in parallel. So the span of that is also going to be constant. Okay. So now combining these three costs again, and again, this should be 2m here. Okay, so we get this recurrence, and solving this recurrence is again a balanced tree because we have one for the parent, one for the child. There are log n levels, so the total cost is O of log n, which is what we expect for scan with a constant span function. Okay, are there any questions on, I guess, finding the costs of sequence algorithms in general for like these functions which have non-constant worker span? Okay, I think looks like we're good on that. So last thing I have for everyone is a practice problem to practice using sequence functions. Okay, so got a problem here called the longest contiguous lexicographical subsequence problem. I'm just going to call that the LCLS problem. So the problem statement is we're given a sequence of characters, and these are all lowercase alphabet from the alphabet, so A through Z. And we want to find the longest contiguous subsequence, which is in lexicographical order. So that means like in alphabetical order, like A, B, C, that order. So for example, if we had a sequence that was like this, the sequence EEGH is in alphabetical order, and it's the longest contiguous subsequence that is in lexicographical order. So for this sequence, the LCLS would be 4. Any questions about this problem? Okay. So you're given two functions. One is like a comparison function, which takes in 2 characters and gives you less, equal, or greater based on the lexicographical order. And you can assume this has constant work and span. And you're also given MCSS, which you should hopefully recognize from the first lab. This takes an int sequence and gives you an int, which returns the maximum contiguous subsequence sum. And this has O of n work and O of log n span. And so given these two functions, your goal is to write a function to compute the LCLS of a character sequence, which returns the length of the longest sequence that's in subsequence that's in lexicographical order. And your function should have O of n work and O of log n span. So I'll give you guys like a few minutes to think about that, and we can see if there are any. Also, if there are any questions, feel free to ask or like put them in the chat, and I'll answer them. The problem again. Okay. Yeah, that sounds like it could work. So I guess, Poon, I think you could definitely make a solution like that, but that doesn't make use of MCSS, so this function that we're given. So I guess that would definitely be a valid solution, but if we wanted to write less code, maybe it could be easier if we could make use of this MCSS, which already does this strengthening, I guess. Okay. Could you expand on what you mean by compare pairs? If in sequence of 1 else 0. Okay, so we got a couple ideas and we're running a little low on time, so I guess I will just talk real quickly about this. So I think, yeah, so what Yunsong said was pretty close. So if in sequence, I think what you mean by that is if like it's greater, if it's lexicographically greater than the previous, then you can map it, or greater or equal, you can map it to 1, otherwise 0. And then do MCSS on that sequence. That's close, except you would always, if you map elements which are not greater, yeah, you would want to map it to negative infinity instead of 0, because otherwise it would always return the entire sequence. With Barat's solution, where you map from 1 to 26, I think, again, you would have an issue where the MCSS of that would just be the entire sequence, no matter what. It would just be like the sum of the ASCII values, basically. But yeah, I think if you adapt Yunsong's solution to negative infinity, so basically if you are lexicographically greater than or equal to the previous element, you get mapped to 1, otherwise negative infinity, then the MCSS of that resulting sequence will be the same as the LCLS of the original. And that's because you're only going to, the MCSS is only going to include elements which are like in order. And then since they're all mapped to 1, summing them up just gives you the length, right? So this would be like, I guess like a pseudocode example of writing LCLS using that index. Okay, and I think it's just about over time. So if there are any questions, I'll definitely stay after and answer those. But other than that, I think thank you guys for coming to the review session. We hope it was helpful, and good luck on the exam.